Welcome to our deep dive.
Excited to be here.
Today, we're tackling Stephen Hawking's A Brief History of Time, a book that's captivated readers for decades.
Yeah, it's a classic for a reason. Hawking dives into those huge questions about the universe, like its origin, evolution, even the nature of time itself.
And the amazing thing is, he does it in a way that makes complex physics, well, surprisingly approachable. I mean, black holes, the Big Bang, it's all in there.
What always gets me is how he starts by walking us through how our picture of the universe has evolved over time.
Oh yeah, starting way back with the ancient Greeks.
Exactly. They didn't have telescopes or computers, but they still figured out the Earth was a sphere.
It's mind-blowing when you think about it. That was a pretty radical idea back then.
Absolutely. And then he takes us through Ptolemy's Earth-centric model.
Which, let's be honest, reigned for centuries.
Right. And then bam, the Copernican revolution comes along. It's all about the sun being at the center.
Talk about a paradigm shift.
It just goes to show, the power of observation and questioning what we think we know. And then, of course, you've got Galileo's observations with the telescope actually backing up that heliocentric model.
That's when things really started to accelerate.
For sure. Then enters Newton, laying the foundation for how we understand motion and gravity.
His laws of motion and universal gravitation were groundbreaking.
Total game changer. I mean, his law of universal gravitation explains why planets orbit the sun in, those elliptical paths rather than perfect circles. It's elegant, but even Newton's theories had their limitations.
And that's where Einstein steps onto the stage.
Oh, yeah. Einstein's theories of relativity, they completely revolutionize our view of space and time.
Special relativity, for example. It's almost impossible to wrap your head around. Time isn't absolute, but relative to the observer's motion.
It's mind-blowing, really. Imagine two people, one standing still and the other moving at high speed. They'll actually experience time differently.
It's crazy to think about. And that's where his famous equation comes from, right? Imensi pocha.
Exactly. That equation basically tells us that energy and mass are like two sides of the same coin. They're interchangeable.
It's like discovering a secret link between two things you thought were completely separate.
Yeah.
It makes you question everything you thought you knew. But Einstein didn't stop there, did he?
Not even close.
Yeah.
He developed the general theory of relativity, which explains gravity in a whole new light. Well, not really light.
What do you think?
It's not a force, but a curvature in space-time. Picture a bowling ball on a trampoline.
Yeah.
It creates a dip, right?
I see where you're going with this.
Massive objects like planets and stars, they warp the fabric of space-time around them, causing what we perceive as gravity.
It's like the universe is this giant cosmic sheet, and objects create their own little gravitational wells. And the craziest part,
What's that?
this mind-bending theory was actually confirmed. Scientists observed starlight bending around the sun during a solar eclipse.
It's incredible. That confirmation led to our modern understanding of the universe, including some pretty wild ideas like the expanding universe.
Hubble's observations played a huge role in that, right?
Absolutely. He observed the redshift of distant galaxies. Think of it like the Doppler effect, but with light. When an object moves away from us, the sound waves stretch out, the pitch gets lower.
Ah, so it's like the sound of a siren changing as an ambulance passes by.
Exactly. Similarly, light from distant galaxies, as they move away, it gets stretched, shifting towards the red end of the spectrum. This redshift told us the universe isn't static, it's expanding.
That discovery blew everything wide open. It means the universe had a beginning, a moment of creation. That's where the idea of the Big Bang comes in.
And there's even more evidence. The discovery of cosmic microwave background radiation.
It's like we're looking back in time.
I know, right? It's a faint echo of the Big Bang, the universe's birth. Hawking's exploration of the expanding universe and the Big Bang is just captivating. And it leads us to another mind-blowing concept, black holes.
Black holes, the ultimate cosmic enigmas. They're formed when massive stars collapse under their own gravity. I still get chills thinking about the event horizon.
The point of no return. Nothing, not even light, can escape its pull once it crosses that boundary. It's a cosmic vacuum cleaner on a grand scale.
But even with black holes, Hawking didn't just settle for the existing knowledge.
He made groundbreaking discoveries. He showed that black holes aren't entirely black. They radiate energy.
It's called Hawking radiation. Mind-blowing.
Before that, we thought they were cosmic sinks, just swallowing matter and energy forever.
But no. Hawking showed that over incredibly long timescales, they slowly evaporate, releasing energy back into the universe.
And that raises even more questions, like what happens to the information that falls into a black hole? It's a puzzle that physicists are still trying to crack.
It's a good thing we have two more parts to this deep dive because we are just getting started.
That's what makes black holes so captivating, you know? They really push the limits of our understanding of physics. It's like they offer a glimpse into some of the most extreme places in the universe.
Yeah, totally. But then, from these massive objects, Hawking takes us to something incredibly small, the world of quantum mechanics. It's a totally different realm.
It's like stepping into a different reality. All the rules we're used to, they just don't apply at that level. In the quantum world, particles don't behave like, say, little billiard balls. They're more like these fuzzy clouds of possibilities.
Fuzzy clouds of possibilities, huh? I like that.
It's where you run into Heisenberg's uncertainty principle. It says you can't know both the position and the velocity of a particle with perfect accuracy.
Wait, so the more precisely we know one, the less we can know about the other.
Exactly. It's not just our measurement tools either. It's a fundamental property of the universe at that scale. It's kind of like,
Right.
imagine trying to track a tiny hummingbird zipping around at super speed.
Okay, I can see where you're going with this.
The more you focus on pinning down its location, the less you can be sure of its speed, and vice versa.
That's a great analogy. And this whole idea of inherent uncertainty, I mean, it really bothered some of the greatest minds, didn't it?
Even Einstein wrestled with it. He famously said God does not play dice because he didn't like this idea of randomness in the universe.
It's pretty incredible that even Einstein struggled with these concepts. But quantum mechanics, as weird as it is, it's proven to be an incredibly successful theory.
Right. It explains all sorts of phenomena, from the behavior of atoms to the technology we use every single day. It's wild.
It's amazing how something so strange and counterintuitive underlies so much of our world. But Hawking takes it a step further. He connects quantum mechanics to even bigger questions, like the nature of time itself.
He explores something called time's arrow. It's this idea that time flows in one direction, from the past to the future.
Oh yeah, like that old saying, time marches on. But Hawking digs much deeper than that.
He does. He talks about different arrows of time, actually. There's the thermodynamic arrow, where disorder increases over time. Then the cosmological arrow, which is marked by the universe's expansion. And then there's the psychological arrow, our perception of time flowing from past to future. What's really fascinating is that these different arrows, well, they might not always align perfectly.
So our perception of time might not be the whole story. It really makes you question something we take for granted. But of course, when we talk about time, there's one question that always pops up.
Time travel. I knew you were going there.
It's just too tempting to resist. Could we actually bend time? Maybe use something like those wormholes we discussed earlier.
It's a really cool idea, but Hawking points out that time travel comes with a whole bunch of mind-bending paradoxes. Think about it. What happens if you go back in time and accidentally prevent your own birth?
Whoa. It quickly turns into a logical pretzel, doesn't it?
Exactly. It makes you wonder if time travel is even possible, or if the laws of physics somehow prevent it to avoid these crazy paradoxes.
Like some kind of chronology protection built into the universe.
Maybe. It highlights how much we still don't understand about the connection between space and time. You know, one of the things that really stuck with me from A Brief History of Time is this idea of the search for a unified theory.
Ah, yes. A theory that could bring together general relativity and quantum mechanics. Those two seem like they speak totally different languages.
It's like trying to get two people from completely different cultures to understand each other. General relativity works great for the large-scale universe, but quantum mechanics is all about the subatomic world. And so far, they haven't really gotten along.
Like they're speaking different languages, as you said. But physicists have been trying to find a way to unify them for decades.
Hawking talks about string theory, which suggests that the universe isn't made of point-like particles, but these tiny vibrating strings.
I've heard about that. It sounds pretty elegant mathematically, but I guess it's still very much a work in progress.
Yeah, it's very speculative. There are other approaches too, like loop quantum gravity, which takes a different mathematical route.
It's really amazing how much effort is going into this quest for a unified theory. It shows how far human curiosity can take us.
Absolutely. It's about pushing the boundaries of our understanding and searching for those fundamental truths about the universe.
It's not just about physics either.
Uh,
Hawking's exploration of this quest really gets into philosophy too. The power of human curiosity, our relentless pursuit of knowledge,
It's about asking the big questions, even if finding the answers is still a long way off. And that leads us to some of those philosophical questions that Hawking weaves into the book. Questions about the nature of reality itself and our place in this vast universe.
Questions like, Why are we here? What does it all mean?
Exactly. He discusses the anthropic principle, which is fascinating. It's the idea that the universe seems almost perfectly fine-tuned for life to exist.
Wait, so you're saying that all these fundamental constants, like the strength of the gravity and the speed of light, they all seem to be set at just the right values to allow stars, galaxies, and ultimately us to exist?
It's mind-blowing. It makes you wonder if it's all just an incredible coincidence or if there's something more to it. Hawking presents both the weak and the strong versions of this anthropic principle. And honestly, they both have some pretty wild implications.
Yeah, the anthropic principle is definitely one of the most thought-provoking things in the book. It really makes you question the nature of the universe and our place in it.
It's almost like the universe was made just for us. But is that really possible? Or is it just an incredible stroke of luck? Hawking doesn't give us a straight answer, does he?
No, he lays out the different versions of the anthropic principle, the weak and the strong, and lets us ponder the implications of each. It's pretty cool.
So remind me, what's the difference between those two versions again? Well, the weak anthropic principle is basically saying that we observe the universe the way we do because if it were any different, we wouldn't be here to observe it. It's kind of a tautology.
You're like, of course I fit in this puddle. If it were any smaller, I wouldn't fit.
Exactly. It's a matter of perspective. We can only observe a universe compatible with our existence. But the strong anthropic principle, that's where things get really wild. It suggests that there might be tons of universes, each with its own set of physical laws.
A multiverse. I love that idea.
It's a mind-blowing concept, and we just happen to be in the one where conditions are right for life.
It's almost like cosmic natural selection. I mean, it sounds like science fiction, but...
But some physicists take it seriously. It really pushes the boundaries of what we think is possible.
And it makes you realize how much we still don't know. There's so much out there beyond our little corner of the cosmos.
It's humbling and exciting at the same time. Hawking doesn't necessarily endorse any one answer, but he does something really important. He invites us to grapple with these big questions.
To think for ourselves, to be curious about the universe and our place in it. And that's what makes A Brief History of Time such a powerful book. It's not just about physics. It's about so much more.
It's about the power of human curiosity, our drive to understand the world around us and our place within it.
Exactly. And, even if we never find all the answers, even if some mysteries stay mysteries.
The journey itself is worth it, wouldn't you say?
Absolutely. Just thinking about these big questions, exploring different ideas, that's what makes life interesting.
And Hawking's book, it's a fantastic guide for that journey of exploration. It shows us that science can be accessible, thought-provoking, and awe-inspiring.
So, to everyone listening, if you're curious about the universe and those big questions we've been talking about, definitely check out A Brief History of Time.
It's a classic for a reason. You'll learn a lot, and who knows, it might even spark your own journey of discovery.
Keep those minds curious, and we'll see you on our next deep dive.